Good morning, everyone. My name is Shivam Nikam, and today I'll present my project on gesture detection using inertial measurement units. This work combines motion sensing, data processing, and machine learning to create a gesture recognition system. Let's dive into the methods, results, and potential application of this exciting project. Introduction to IMU based gesture detection. Gesture recognition is revolutionizing human computer interaction by enabling hand free control. IMUs, which are equipped with accelerometer and gyroscopes, are ideal for capturing motion data because they track acceleration and angular velocity across three axes. In this project, I focused on designing a system that utilizes the MPU 6050 IMU and ESP32 microcontroller to classify gestures in real time. Although position tracking was initially considered, we shifted the angle-based recognition due to the challenges posed during the drift and error accumulation in position data. Our primary objectives were to collect and process motion data using MPU 6050 sensor and ESP32 microcontroller, to implement calibration filtering techniques for accurate data collection, to classify gestures using machine learning models like KNN and support vector machines. To demonstrate the system's potential through practical application, a gesture control calculator was made. Our system architecture is straightforward. The MPU 6050 sensor collects raw acceleration and angular velocity data. The ESP32 microcontroller processes this data and transmits it wirelessly to the PC using Bluetooth. The PC processes the transmitted data for gesture classification and application control. Accurate data is backbone of gesture recognition. To achieve this, we applied the following techniques. Calibration. We calculated three methods: mean calibration, linear regression, and polynomial regression. Among these, mean calibration provided the best balance of simplicity and effectiveness by reducing systematic errors in sensor data. In filtering, to minimize noise, we tested Kalman filter, complementary filter, and low pass and moving average filters. Kalman filter is selected for its ability to dynamically correct noisy sensor readings, offering high stable results. Complementary filter is easier to compute but less precise. Low pass and moving average filters are good for noise reduction but slower in real-time response. Here are the graphs which I have used to filter the data. In this graph, I have moved the sensor in x direction forward and backward, giving us these peaks. And as these peaks are generated, the displacement is being integrated continuously, hence offering this extra area which has contributed to the displacement. And because of this, real-time position tracking was not being able to achieve using MPU 6050. That's why we transferred our focus to gesture recognition. We used Kalman filter for processing the data. This is the difference between raw and filtered data which was achieved, but even after filtering, there was still noise which were getting accumulated, and because of the integration in displacement, this data continuously accumulated along the time and increased our displacement which was not even there. To recognize gestures, we calculated angles such as pitch, roll, derived from the filtered accelerometer and gyroscope data. These angles represent the tilt and orientation of the sensor, form the basic for the gesture classification. This is the roll, as you can see. This is the pitch and this is the yaw. Yaw's data was not accurate enough for us to filter out. So we have just used roll and pitch in this condition to get points which we need. These roll and pitch data were obtained using Kalman filter. Kalman filter is an algorithm that provides accurate state estimates by dynamically correcting sensor data with uncertainty models, but requires significant processing power. There is another filter which is common, that is complementary filter. The complementary filter combines accelerometer and gyroscope data for efficient real-time orientation tracking with minimal computation, but lacks the precision and adaptability of Kalman filter. Now, through my observations, what I observed was after I tilted my sensor to, let's say, 30 degrees, the Kalman filter gave me faster updation of readings, while the complementary filter was still at still in the process of giving me the degree. That's why I found this slower. And as I was capturing my data, the the gestures which had to be recorded were being delayed. That's why causing uncertainty in our gesture recognition. That's why I shifted to using Kalman filter. I used calibration methods like mean and ML algorithms, but later I decided and fixed my calibration to mean because it was simple and gave better results. The machine learning models I use for gesture recognition. To classify gestures, we implemented two machine learning models, KNN and SVM. KNN is a simple non-pragmatic algorithm that classifies data based on its proximity to other points in 4D space. Each gesture, such as swipe up, swipe down, or circle, is represented by a vector of tilt values. For example, when a new gesture is performed, KNN calculates its distance to existing data points and assigns the gesture based on majority voting among the nearest neighbors. The strength of KNN are its simplicity and effectiveness for small datasets. However, it can be computationally intensive for larger datasets. During my trial study of KNN versus SVM, I found out that KNN consistently achieved higher accuracy, especially for simple directional gestures like swipe left and swipe right. SVM performed well in some cases, particularly with linear kernel, but struggled with more complex gestures like circles. This demonstrated that while KNN is simpler, it's better suited for a specific dataset and real-time requirements. This project had many challenges. Like I mentioned earlier, there was drift in position tracking. There was also a computational load, which I had to design the dataset myself to get the gestures easily recognized. And there were many overlapping gestures because of the smaller neighboring values. But I had tried with many neighboring values. I tried with 1, 2, 3, 4, and 5, but I found that 3 gave me the most accurate results comparatively to the others. Using this, I developed swipe up, swipe down, swipe right, swipe left, and circle. And I also added two more gestures, which was fast forward left and fast forward right. Swipe up is same gesture which you generally do on mobile, that is tilt the sensor to upward direction. Swipe down is swipe the sensor to a downward direction. Swipe right is swipe the sensor to rightward, and swipe left is swipe the sensor to left. Circle gesture is a little bit complicated. If this is the MPU sensor, what you have to do is tilt the circle forward, leftward, backward, and downward to get the circle movement. And fast forward left is a simple circular movement which you do on in front of your face. So for fast forward right is clockwise, and fast forward left is anti-clockwise. With these help of gestures, I designed a gesture control calculator. To showcase the system's capabilities, we developed a gesture control calculator. Here's how it works. Circle gesture switches between the modes such as storing operands or selecting operation. Swipes, swipe up for addition, swipe down for subtraction, swipe left and right to decrease or increase the operand values. And advanced gesture like fast forward gesture was integrated to handle modulo and power operations. The calculator provides a hand-free, intuitive way to perform calculation and demonstrate system's practical potential. There are a wide range of applications and future work that can be done in this project. This system has wide-ranging applications as you have seen. It can be an assistive device for physical disabilities. It can also be used for gaming and virtual reality. It can also be used for industrial automation, like hand-free controls in manufacturing and robotics. And in future, it can be also expanded to support more complex gestures using neural networks, integrate haptic feedback for more interactive application, scale to full body motion tracking for VR and sports training. I would like to conclude my project. In summary, this project developed a robust gesture recognition system using the MPU 6050 IMU and ESP32 microcontroller. By employing advanced calibration, filtering techniques, and machine learning models like KN and SVM, we achieved reliable and accurate results. The gesture control calculator highlighted the system's real world potential, paving the way for further innovation in wearable and interactive technologies. I would like to thank my advisor, Mr. Arun Raman, for his invaluable guidance throughout this project. I also want to express gratitude to my family, friends, and the opening source of community for their support and resources. Now, after this presentation, you will see a live demo of me performing gesture recognition using the IMU. Thank you. Today, I will be giving the demo for my gesture detection IMU. It is training the KNN model right now and so also calibrating. The calibration is finished. Now the gesture detection will start. Now let's try swipe up. Okay, it has worked. Now let's try swipe down. Now let's try swipe left. Now let's try swipe right. Now let's try a difficult one, which is a circle. Let's hope we get it in first try. I knew it won't be. Let's try it again. Okay, we got it in second try itself. Now let's try something more difficult. Let's try fast forward. Oh, it worked. Now let's try the other way around. Oh, it worked. Okay, so this is all with the demo. So I'll be closing this.